So in this video, I'd like to make a wish list. So let's pretend it's Christmas time. So let's say we're given some ring, and what are some qualities of that ring that would be desirable? What properties would we like that ring to have? So I say R is some ring, is a ring. Let's say that one desirable quality of R would be that it has a unity. So we could say unity. We've also talked about commutative rings. So it would be nice if it was commutative. Commutative. Actually, unity or a 1. You'll hear both of them, unity or 1. Other desirable qualities. Well, the last video I just did was on zero divisors, so maybe no zero divisors. No zero divisors. And if you were paying attention in the last video, you would actually see that these three properties right here would make this an integral domain. Integral domain. If we have those three properties, then R is an integral domain. Is there anything else that that would be desirable, a desirable quality for R? Well, since we have a unity, maybe having some multiplicative inverses would be nice, or another word for that is some units. So, well, actually, not just having some units, but maybe having every element in the ring has or is a unit or has a multiplicative inverse. So let's say every element is a unit. So I mean, I just made this up. This is a wish list that if R is a ring, or if we're handed a ring, then it would be nice if it had these four qualities. And a ring that does have these four qualities, we would call a field. A field. So a field is an integral domain. Integral domain where every element is a unit. Every element is a unit. Now, do we have any examples of this? Well, sure. Let's say the real numbers. Real numbers are a field. The real numbers, from the last video, we saw they're an integral domain. They have a unity. It's just plain old 1. Let me do this in, let's do green. They have a 1. They are commutative, so 2 times 3 is the same thing as 3 times 2. Real numbers are commutative. There are not any zero divisors, so if a times b equals 0, this implies that either a is 0 or b is 0. So there are no zero divisors in the real numbers, the ring of real numbers. Also, every element has a multiplicative inverse. So say we have 4. We want to multiply 4 by something to get our unity, which we said was 1 right here. So we want to multiply 4 by something to get 1. Well, that would be 1/4. And 1/4 is a real number. So 4 has a multiplicative inverse, or 4 is a unit. And there's nothing special about 4 here. You could pick any integer. So a, and any real number a. And to find its multiplicative inverse, you would just do 1 over a. That would give us 1 in the real numbers. So the real numbers form a field. So some more examples. The rational numbers also form a field. There's not really much different happening other than instead of real numbers, you have rational numbers. That all of the same stuff holds pretty much. Other examples, complex numbers. Complex numbers form a field. if you remember from the last video, z sub p, where p is prime. Z sub p will be a field. That one's a little harder to see. The multiplicative inverses in here, it might you might hesitate on calling that a field, but it is a field. If you can verify that if you want. Some examples of things that are not fields. The integers. Integers are not a field because we don't have multiplicative inverses. We have the rest of this, so they are an integral domain. We have these three qualities, but they do not have multiplicative inverses, or at least not every element has a multiplicative inverse. Other examples of things that are not fields, z sub c, where c is composite. Likewise, this is not an integral domain because it does have zero divisors. One more example I can think of, the set of all 2 by 2 matrices with coefficients from, I don't know, we could say R. This is not a field. It's not even a commutative ring. So it's not an integral domain. It's not commutative, so it's not a field. And one last thing I can think of to say about fields for now is we have this theorem. It's kind of useful to know, but it's not really anything too special. And it says that a finite integral domain, in other words, an integral domain with a finite number of elements, a finite integral domain is a field. And I'm not going to prove this, but again, I just think it can be useful to know in certain situations. So I will leave you with that, and I will see you in the next video. Actually, one more thing that I should probably mention. There's a whole theory out there behind the study of fields, and even though we are studying rings right now, fields are very important. They come up quite a bit, and so we really should define them and kind of know what we're dealing with here. So we're actually not studying fields right now, but they do come up quite a bit in ring theory.